Hi, everyone. Can you hear me? Hey.
Yeah.
Can I ask everybody to turn on their videos so I can see you guys? So, okay, so I know I've been speaking to several of you about progress on the projects, etc. So actually, you know what? Let's just go down the list. We'll give everybody another 2 minutes to join, and then we'll just go through the various projects. Make sure that you've uploaded all documents or linked them to the website, the Google Doc. I'm having some connection trouble, so I hope they don't get worse. Actually, hold on 1 second. Let me reduce my screen resolution so it goes a little faster. Okay. So, first of all, who wants to go first? Who has the most stuff to talk about and issues that they would like to sort out? And can I ask everybody to just rename your screen name with the number of your team, like 13-Joe, etc., or 11-, so I can much more easily and rapidly look up your teams. Okay, so is there anyone from team 1? You know what, let's go with team 5 since you guys seem to have a lot of folks. So Stephanie, Kathleen, and Alice are all there. So let's look at the Midcourse report. Ta-ta-da.
Oh, we changed our project, so the proposal and the pipelines are not.
Okay, okay. So this is the project now? Yeah, perfect.
Yeah.
Cancer classification on single cell RNA-seq graph neural network approach. I'm sorry, when I actually have access, I end up doing things like, you know, changing the formatting. It's funny that the default that it goes to is in fact cans instead of okay. Mind if I do something funny like use my default styles? Cool. Okay. Oh, this is very cool. So you've got the data and you've already started playing with the data.
So we try with RNA-seq first because that's what the paper did. And then we also have collected scRNA-seq, so we can just apply the method on the scRNA-seq data.
Great. Okay, cool. So basically first classification, then compare the performance with the results of the study, patterns among. So what I would also say is so perhaps also add what does the set of selected features tell you about the biology of what's being selected? So basically, can you somehow gain some insight as to, you know, study what are the important features through the GNN? So, i.e., perturb the input and study how the output changes versus each feature and infer from that the importance of each feature or classification of each answer type. You see what I mean?
Could you explain more on what it means to perturb the input?
So basically, there's many ways that you could figure out which features are important for deep learning model. One of those ways is to look at the weights. Another way is to look at how the performance changes when you manipulate different inputs. So you basically have your whole tree of you know, features getting wired together into stacks. And then what you can ask is, if I perturb one of them, then how much does the output change? Instead of trying to trace through the weights what are the important features, you can actually just actively change each of the genes, like double the size of the gene and then see whether the performance changes. If it doesn't, that basically means that that gene is not an important feature. Does that make sense?
Yeah, gotcha.
Yeah. Yeah. So basically beyond weights, okay. So I think you guys are in very good shape considering, you know, that you've started from scratch. And again, I'm so glad that we started early because you actually can do that. And I think this is great. Do you have any questions for me, or are you guys sort of on good track now? Good track?
Yeah, I think we're, yeah.
Okay.
Yeah, thank you.
Of course.
Thank you so much.
So this was team 5. Okay. All right. So I see Jejen, are you there? So Jojo, are there any other folks from team 1?
Nope, I think it will be me for today.
Okay. So are you guys taking more or less the same project?
Yeah, we're still doing the same project.
Yeah. So remind me where your data is coming from?
Our data set comes from both bulk ataxic, single cell ataxic of AML cells. And we also combine with the transcriptional system-wide transcriptional profile from one of your previous study.
That's great. Perfect. Oh, cool. You already built a model. This is awesome. What does 60% 2020 mean?
Oh, sorry. It's the amount of total data we used.
I see. Great. Cool. So is it working?
Unfortunately, no. And I think that's our main issue right now.
Yeah. So have you tried it on smaller, easier problems? Like basically you could construct a planted data set to make sure that at least the code is working. And
So maybe we can generate a synthetic data set.
exactly.
Oh, yeah. Yeah, that's actually a good suggestion because we are worried about our bulk training data.
Can you give me edit access so I can
Oh, yeah, sorry. Yeah.
I sent you a request. If you add manoli@gmail.
Yeah, I think you are added right now. Thank you.
I reload it. Hopefully that'll give me access.
Oh, sorry. Can you make change now or?
Let me try again. Okay, yeah, now I can.
Okay, sounds good.
Make sense? So basically you can make it progressively harder. So at the beginning, make it super easy to make sure that it works. And then sort of you can say, well, up until what frequency can I still detect them? And so on and so forth.
Yeah, that actually sounds like a really good suggestion because we were kind of
Then we
struck
can
by.
decouple basically how much of it is coding versus how much of it is biology. Yeah, awesome. So basically once you've tried that, then we'll know what's going on and then we'll proceed accordingly. Okay.
Sounds good.
But
Thank you.
You know, let me know if you guys have more questions after that.
Mm, sounds really nice.
Okay.
Thank you very much.
Thank you. Okay, so is anyone from team 2 there?
Yeah, Mindran and I are both here.
Okay, perfect. Sounds great. So, and you guys are still doing the same project?
Pretty much, yeah.
Oh, yeah, perfect. The aging clock. So did you talk with, so did you follow up on what we talked about last time? Does it make sense? Oh, I had an amazing idea. You guys will love it. Are you ready?
Sure.
So the GTEx project also has telomere length. So one of the projects in GTEx is actually looking at telomeres. So what you can actually do is ask if the telomeres in each cell can be used as a surrogate for age of that cell or of that tissue. Does that make sense? So one suggestion would be, use perhaps check if telomere length is available for a subset of individuals in a subset of tissues. Perhaps use the telomere length-based age prediction as the gold standard for training, or perhaps validating, your prediction in each tissue. Does that make sense?
So you're saying to train the model just using the telomere length alone, or are we using it like in conjunction with
Okay, so
the
let's
other expression data we had?
you could say train a model for age in each tissue independently based on chronological age. B, train a model based on telomere length directly. C is train a model of age, tissue age prediction from telomere length and use the telomere length based prediction of tissue age as the age for the expression rate. So all of the above. Basically, multiple options, but you can play them off each other. It was just one more idea. But what we discussed yesterday still holds, right? So
Yeah, that makes sense. Thank you.
is this sort of based on our discussion, or is this before?
This is sort of, I guess, those preliminary results are just using genes directly with the chronological age in those particular tissues.
This is fantastic. This is looking really lovely. You guys are happy?
There's good progress, I think. Oh, I just showed it, I think, too.
Yeah, and I think you can.
Do you have anything to add?
You can still follow up on the, sort of also, as we discussed, compare relative ages of each tissue with each other. Okay. Feeling good?
Yeah.
Cool.
That's good, thank you.
Looking good, guys. Let's see. Team 3. Landon, Ari, are you guys there? Team 4. Sonia, Lily, Jonathan. Team 5, we talked. Team 6. Anybody there?
Yeah,
Okay,
I'm
perfect. We got Pablo's. And then okay, deep learning SRNA-seq batch correction. Very cool. I love it. How are you guys doing?
We're doing okay. We've built our deep learning model, and we have some preliminary results, but they're not really valid because we're using like Euclidean metrics to sort of evaluate it, but our deep learning model doesn't really operate in Euclidean space. So we still have to like develop sort of a conversion so that our metrics will make.
But you can still use a Euclidean evaluation for a non-linear model.
Yeah, well, but I think like
because that's about the distance metric between your predicted and your goal, and that distance metric could be anything. It can be linear, non-linear, you name it, right?
But I think it's because like with our autoencoder, like we're making like a smaller embedding, and that doesn't necessarily correspond like linearly. I don't know. I'm not like, I've been working mostly on the metric side, so like my other teammates know a little bit more about this problem that we're facing. But I think I think the project is in a good place right now. We have like our metrics and stuff ready.
Okay. And you have stuff running and working?
Yeah, if you scroll down to preliminary results.
Ah, perfect.
Yeah, so there's a bunch of notebooks in here. If you look at the metrics one,
Yeah.
there, in there we have,
How am I supposed to open this?
well, I've opened it in, can you open it in Google Collaboratory?
Oh, okay.
Yeah, so this is from Harmony, which is one of the papers we're basing it off of. So that was the original cluster, and then here's harmonized. The clusters are much more defined.
Yeah,
And
yeah.
then, but that's just using PCA. So then these clusters are with our autoencoder, which
Oh,
as you,
interesting.
huh?
And what do the clusters look like without your autoencoder?
These are the ones with PCA.
I see. So this is with PCA,
Yeah.
and
And
then
then and then this is PCA, but it's harmonized, which is one of the papers that we're basing it off of for batch correction.
yeah,
And then what we're trying to do here is instead of PCA, use our autoencoder.
yeah,
And as you can see, it doesn't look like it's working as well right
yeah,
now.
yeah. But again, I mean, I think that you have things in place to sort of make it work. Like
Yeah,
basically,
so
right
we're still working on it, but that's
Yeah, but basically you're past the logistics. Now it's really science. So it's
yeah.
yeah, that's awesome. Very cool. Good. So basically you're at the stage where if it works, then you can do all kinds of really cool things. But
Mhm.
until it works, you still don't know if you have a successful project, basically.
Yeah.
There you go. I would say, let me know as soon as it does, because then based on the results, I can give you a bunch of suggestions for where to go next.
Okay, yeah, we'll
Yeah.
let you know.
But right now it's looking good. Good. Okay, so let me just increase this a little bit. Okay, so now next is team 7. Did we talk with 7 or actually no?
Yeah, we're here.
Okay, perfect. Okay, let me close the other ones. Perfect. Pablo, did you have any other questions?
No, I don't think so. That's
Okay,
good.
perfect. You guys are feeling comfortable?
Yeah, I think it's in a good place.
Okay,
Yeah.
that was great. I'm in trajectory. Beautiful. Oops. Nice. So tell me a little bit about how you guys are doing. So, it seems like you have all the pieces together, right? Like the pseudo time, or sorry, the yeah, the pseudo time seems to be working, and you have data, you've been running your code. I mean, are you feeling pretty awesome?
We are actually kind of lost in terms of like interpreting the monocle trajectory because each time we run, it will give out a different trajectory. So we are wondering like which one is biological meaningful.
Yeah. So basically, let me put it in slightly different terms. You have the code ready, you have the data ready, you have everything running, and now you're at the stage of interpretation. Basically, does it make
Yeah.
sense? Is this real? And why is it
Mhm.
giving you different things each time? So basically, I think the way that you should think about interpretation is project it onto a space that kind of makes sense biologically. And it's possible that even though you have different trajectories, that they project into the same space in the same way. Okay, so basically what I would say is for interpretation, ask which pathways change first. If you plot, let me scribble. If you plot a trajectory with time being this way, and then you ask what's pathway 1 looking like, what's pathway 2 looking like, what's pathway 3 looking like, so you could then sort of pathway peaks in activity. Let's see, stop share this instead. You see what I'm getting at with this? So if you project each pathway along the time course do the same pathways, peak early versus late in different monocle paths. Do you see what I'm getting at? So basically, don't worry about the specific path as long as it takes you through. Mais du côté jardin. Ça marche. Okay. Hold on 1 second, guys. Okay, just 1 second, everyone. I'm so sorry about that. Hey guys, I'm back. Sorry about that. Does it make sense? So basically the question is, it's not the exact same path, but as long as the biological quote unquote projection of that path is still making sense. So suppose that you're building two different paths, and in both paths, the same pathways are sort of lighting up first. Do you see what I'm getting at?
So like, what do you mean by different path? You mean different plots or like different?
So you know what Monocle is doing is sort of creating a path effectively through the cells. Basically, as you start here and you move through there and so on and so forth, right? So my question is, you know, I mean, these paths actually look identical. So you're just coloring them in different ways, right?
Oh, the right one is colored by time. So we set the root nodes, and then the root nodes is starting from time 0 and it's going the other way.
So then the question is, you know, as I move along this, so now I take this path and I project it onto a linear space, right? And then I can ask, how are different pathways expressed along this linear path?
Okay.
You see what I'm getting at?
Okay, kind of.
Yeah. Rolled out onto a linear plot, right? From 0 to 30 on the x-axis. And that's the 30 that comes from the pseudotime.
Okay.
Okay, do you have any other questions as to sort of, so basically the challenge that you guys have now is that pseudotime kind of seems to be switching each time. Yeah. So that's the thing, basically check if the switches are actually biologically meaningful or not. Because it's possible that it's switching in a way that's invariant to the biology, or it could be that it's switching in a way that makes completely different inferences as to what are the pathways and genes that light up first or second.
Okay. Okay, we'll try it out first. Yeah, thank you.
Awesome, thank you. Good, so let's go back to team. Team 8, Audrey, Michael, Pia, are you guys there? Team 9, Tom, Wendy, and Hugh. Team 10, actually, sorry, Team 11, Erez, Joanna, and Ricard. I mean, we talked yesterday. Christian and Andrew, are you there? Manvita, Kamal, Joe?
Yeah, we're here. Hi.
Hey, how's it going? All right.
Good.
So are the drug repositioning slides still relevant?
Oh yeah, so we've pivoted back and forth, but now we're on this is like the original thing before I joined into teams. It's complicated. Now we're on graph neural networks learning on drug reversing. Yeah. Should we be updating these old proposals and the slides?
Oh, no, no need. Basically, I mean, unless you feel like it, but basically it's just it's helpful for me to get a sense of where you were and where you're going. But in the end, it's only your final report that matters, basically. So as long as that's, you know, getting updated. And then ultimately you'll make some slides for your final presentation as well. And then these will supersede your slides from the original one. It's just that not everybody puts a ton of background on the final report. That's why I see the other ones first. Does that make sense?
Mm-hmm.
Okay, so how far along are you? How are things?
So we're doing like a whole bunch of models in parallel, like some simple models that are working perfectly, some more complicated models that are not working yet.
Yeah.
And the simple modeling approaches, which use graph neural networks to do multimodal edge prediction for drug repurposing, is working fine. And we're going to use this in terms of like sort of transfer learning tasks where we do COVID drug repurposing stuff.
You guys are in such good shape. This is really looking great. Cool. Do you have any questions for me or?
No.
Okay.
I think Manu is also online but I'll let you know.
Okay, perfect. Cool. And then Na, Juna, Guillaume, Fatima, are you guys there? And anyone who hasn't gone yet? Okay. I see Jose. Jose San, which team are you in? Okay, so yeah, basically, I think you know, you guys are in good shape. Again, my goal is to give you feedback along the way and sort of check where you're standing. If you guys have no other questions, we can just, you know, wrap it up. Okay, awesome. Thanks, everyone. Looking great. Very good progress for all the folks that I spoke with. Thank you. Bye.
Thank you. Thanks.
Thank you.